So ARIMA stands for Autoregressive Integrated Moving Average, and it is, in my definition, a way to forecast future values using existing past data on the same type of values. And what I mean by that is, for example, in order to forecast stock prices or stock values, we base that forecast based on past stock values. And a wrong example would be forecasting stock values based on oil prices, which are completely different factors. And so the ARIMA model has three components: the autoregressive component, which is shown as P, moving average component, which is shown as Q, and the differentiation level, which is shown as D. And so usually when we describe one ARIMA model, it would be written as ARIMA parentheses P, comma D, comma Q. The ARIMA test is to find the differentiation level. So in order to do that, you click on whatever work file you're going to use and the time series work file, and then you go to View, Unit Root Test, choose Standard Unit Root Test, and then it'll automatically have Augmented Dickey-Fuller as a default. And then for the first time around, you want to choose Level so that we can check whether we don't need any differentiation at all. But if you but you'll later notice that like maybe you do need to do a differentiation, and I'll explain why later. But like yeah, you can choose that first difference or second difference. But yeah, the first round you just keep it at level, and then you press OK, and then you get this. So we mainly look at the p-value here. So the p-value here is 0, so that means that we don't need to do another differentiation. But sometimes this part, if the p-value is greater than 0.05, then that means that you do need to do a first differentiation. So try doing that, and if the p-value then is less than 0.05, then you're good to go. So before we go into parallelograms, I want to describe what ACF and PACF are. ACF is autocorrelation function. It basically measures how strong a value is correlated with one another value from a period in the past. And PACF is how strong the current value is correlated with the one other value, but also taking out the influence of other values from the other periods in the past. We're going to create the parallelogram. You go to View, and then go to parallelogram, and then you enter the level of differentiation that you found out from the last step. And for this data set, we didn't need to differentiate at all, so we keep it at level, and then we click OK, and we get the parallelogram. So the interpretation of the parallelogram is where data science really becomes an individual art. And so we see that in this graph, the 7th lag shows a significant level as the parallelogram exceeds the significance level line. And so I'm going to do AR 7 and MA7. How I determined this is from the because the most significant value is on the positive side, and for the first time it exceeds significance at lag 7. And if you want to include more lags, then you are free to do so, and that is your individual choice. I also want to quickly note that if there are no significant values in neither ACF nor PACF, then you have a white noise data, which means that there are no significant results that can be had from the data because there's nothing significant. Do the ARIMA forecasting. So in order to do that, you go to Proc, Automatic ARIMA Forecasting, and then we altered this part. So what we found is that we don't need to difference at all. And then the max AR will be 7, max MA will be 7. And then SAR is about seasonality, which is kind of out of the scope of this video. And as for the estimation sample, we set it at, let's say, we want to forecast 4 months, then we can just do 2012 month 12, and then we say forecast length 4, and then okay, and then it'll take a little bit to forecast, but we got the results, and yeah, that is our forecast model.